Where is everybody? It is perhaps the most profound and haunting question we have ever asked of the cosmos. We stand on a tiny, fragile world, orbiting an unremarkable star in a quiet corner of a galaxy that contains hundreds of billions of suns. And that galaxy is just one of trillions adrift in the observable universe. Given these staggering numbers, given the sheer statistical noise of possibility, the silence we are met with is deafening. It is a silence that has been given a name, the Fermi Paradox. For decades, we have treated this question as a puzzle for biologists, for sociologists, for philosophers. We've wondered if life is rare, if intelligence is a fluke, or if civilizations inevitably destroy themselves. We have looked for answers in the chemistry of distant atmospheres and the abstract models of societal collapse. But what if we've been investigating the wrong crime? What if the absence of evidence isn't evidence of absence, but evidence of an engineering challenge so monumental, so fundamentally crushing, that virtually no one in the history of the cosmos has ever surmounted it? What if the great silence isn't a biological or sociological mystery, but the single greatest engineering problem in the universe? This is the thesis of our investigation today. We are recasting the Fermi Paradox. It is no longer a passive question of, where are they? But an active, urgent engineering challenge. How do we build something that makes our presence known across the stars? The problem isn't that the universe is empty. The problem is that the universe is big, and the tools we assume a civilization would use to communicate are catastrophically, almost laughably, inadequate for the task. We are detectives, and the scene of the crime is the entire cosmic landscape. The victim? The idea of a connected galactic civilization. The cause of death? The tyranny of the inverse square law and the overwhelming, crackling noise of space-time itself. For too long, we have been like a tribe on an isolated island, shouting at the ocean and wondering why no one from across the horizon shouts back. We have failed to appreciate that the ocean is not a quiet pond. It is a perpetual, galaxy-sized hurricane. Our shouts, our radio signals, our most powerful transmissions are less than a single raindrop in that storm. They are whispers consumed by a cosmic roar the moment they leave our world. Let's put this into a true engineering perspective. Imagine you're trying to read a single word, written on a single grain of sand on a beach in Brazil, while you are standing on the moon. That is the scale of the difficulty we are talking about when we hope to detect a directed radio message from a civilization a few hundred light years away. The energy required to send a signal that remains intelligible over interstellar distances against the background noise of pulsars, quasars, and the cosmic microwave background itself is staggering. It is a brute force energy problem of the highest order. A civilization would have to focus a significant fraction of its star's energy output into a single, tight beam pointed at us for a specific period of time, just for us to have a chance of noticing it. And this assumes we are looking at the right place, at the right time, with the right frequency. It's not looking for a needle in a haystack. It's looking for a specific atom in a mountain of needles. From an engineering standpoint, it is a communication strategy defined by its inefficiency. So, why would a truly advanced, intelligent civilization, a civilization of engineers, rely on such a primitive, hopeful, and ultimately flawed method? The answer is, they wouldn't. This is where our investigation truly begins, by throwing out the old assumptions. We must stop thinking like islanders, shouting at the waves, and start thinking like cosmic engineers. The solution to being heard across a hurricane is not to shout louder. It is to build a lighthouse, a structure so immense, so energetic, so fundamentally reality-altering that its existence is the message. A signal that doesn't need to be decoded because its very presence is an undeniable statement of intelligence, of power, of existence. This is the core of our blueprint. The answer to the Fermi Paradox lies not in communication, but in construction. The evidence we should be looking for is not a whisper, but a shadow, the shadow of a megastructure against the light of its parent star. Today, we are drafting the blueprint for this cosmic lighthouse. We will explore the engineering requirements for a project so vast it would reshape a solar system. We will investigate the materials science, the energy logistics, and the orbital mechanics required to assemble a structure on a scale that borders on divine. We are moving beyond the philosophical and into the practical. The great filter, that theoretical barrier that stops civilizations from becoming interstellar, may not be a meteor, a war, or a plague. The great filter may, in fact, be a final engineering exam, a test of a species' ability to harness the full potential of its star and its solar system, a test that, as far as we can tell, no one has yet passed. Our mission is to understand the questions on that exam, to reverse engineer the challenge from the silence we observe, and in doing so, to write the first draft of humanity's answer. The blueprint we will lay out is more than just a theoretical exercise. It is a roadmap. It is a declaration of intent. It is a statement that says, if the universe is silent, it is not because it is empty, but because no one has yet had the courage, the vision, and the engineering prowess to build loud enough. We will not be another whisper in the storm. We will become the lighthouse, and our light will be the undeniable proof that intelligent life is not just a fleeting accident, but a cosmos-shaping force. This is the legacy of the stars, and the frontier of cosmic engineering we are about to cross. The investigation into the blueprint begins now. Before we can draft a blueprint for success, we must first study the anatomy of failure. Any engineer, any detective, knows that you cannot solve a problem until you respect its scale. And the problem of building a cosmic-scale megastructure is one of such profound, multi-layered impossibility that it borders on the absurd. We are not talking about building a taller skyscraper or a longer bridge. We are talking about defying the very principles that govern construction on a planetary and even stellar scale. This phase of our investigation is a deep dive into the abyss of the impossible, a meticulous documentation of the forces that make the great silence the predictable default state of the cosmos. Let us begin with the most brutal and uncompromising of all constraints, the sheer, soul-crushing problem of mass. When we speak of a Dyson sphere or a similar megastructure, what are we actually talking about in terms of materials? The numbers are so large, they become meaningless without analogy. Let's consider building a relatively modest structure, a solid shell around our sun at the Earth's orbit. To give it a thickness of even a few meters, enough to be structurally sound and provide shielding, would require a mass that dwarfs anything we can comprehend. You would need to dismantle not just Mercury, not just Venus, Earth, and Mars, but the entire asteroid belt, Jupiter, Saturn, Uranus, and Neptune. You would need to harvest the mass of every planet, moon, and rock in our solar system, and you would likely still come up short. Let's make that more relatable. The total mass of every single thing humanity has ever built, every city, every road, every ship, every satellite, is estimated to be around 1 trillion tons. That is an impressive number for our civilization. But the mass of Jupiter alone is 2 quadrillion trillion tons. You would need to multiply humanity's entire industrial output by 2 trillion just to equal the mass of a single gas giant we'd need to consume as raw material. And so what? Why is this a problem beyond just a big number? Because mass is intrinsically tied to energy via the unforgiving laws of gravity. Every kilogram of that material is currently sitting deep within a planetary gravity well. To lift it, to move it into a construction orbit, requires energy. The rocket equation, the fundamental tyrant of space travel, tells us that for every unit of mass you want to move, you need many more units of propellant. To liberate the mass of Jupiter from its own gravitational pull would require an energy expenditure that beggars belief. We are talking about capturing the entire output of the sun for centuries, if not millennia, just to power the fleet of machines needed to deconstruct one planet and move its constituent atoms into position. It is a logistical and energetic barrier, so high that it acts as a perfect filter. Any civilization that cannot command the energy of its star cannot even begin to gather the raw materials. It is the universe's first and most profound engineering checkmate. You cannot build the star harvesting machine without first having the power of a star harvesting machine. This single recursive problem of mass and energy is, for most civilizations, the end of the story. But let's assume, for the sake of our investigation, that a civilization overcomes this. Let's say they have limitless energy. They have disassembled their solar system and have trillions upon trillions of tons of refined material ready for assembly. Now they face a second, more insidious barrier, the limits of matter itself. What do you use to build your sphere? Steel? Titanium? Diamond? It doesn't matter. Every material you can imagine, from the mundane to the exotic, is held together by electromagnetic bonds between atoms. And these bonds have a breaking point. We call it tensile strength. This is the H in why this is impossible. A solid, rigid Dyson sphere is a physical impossibility. The gravitational forces exerted by the central star would not be uniform across the structure's surface. The slightest deviation would create stresses, shear forces that would rip the sphere apart. Furthermore, the internal pressure of the sphere itself, the tendency of a sphere to want to expand outwards, would be colossal. No known or even theoretically conceived material could withstand it. Carbon nanotubes, often hailed as a miracle material, are incredibly strong for their weight, but they are not infinitely strong. Building a solid sphere around the sun would be like trying to build a dome the size of the Earth's orbit out of spider silk. It would collapse under its own conceptual weight before the first piece was even in place. So, a solid sphere is out. What about a ring world, a spinning habitat that creates artificial gravity? Here, the problem is even more acute. To simulate one Earth gravity, a ring at Earth's orbit would need to spin at a velocity of over 1,200 kilometers per second. The centrifugal forces, the tendency of the ring to want to fly apart, would be so astronomically high that they would overcome the atomic bonds of any conceivable building material. The ring would need a tensile strength thousands of times greater than that of pure diamond. The atoms would literally be torn from their neighbors. The structure would vaporize into an expanding cloud of its constituent particles. It's not a matter of poor design. It's a matter of fundamental physics. You cannot spin a structure that large, that fast, without it destroying itself. This isn't a problem you can solve by adding more support beams or using thicker plates. It is a hard, inviolable speed limit imposed by the universe on the integrity of matter. The very act of making the habitat livable is what guarantees its destruction. This is the second engineering checkmate. Let's press on. Let's imagine a civilization has found a way around this, perhaps with some form of exotic matter or force fields, a topic for a later phase of our investigation. For now, let's say they have their materials. They are building their structure, not as a solid object, but as a swarm of individual habitats, a Dyson Swarm. This is the more plausible model. But even here, the challenges are monumental. The structure is now not a building, but a dynamic system. It is the single largest and most complex machine ever conceived. It consists of billions of continent-sized power stations and habitats flying in close formation, all orbiting a star. The orbital mechanics of this system are a nightmare. Each component is tugged by the gravity of the star, but also by the gravity of every other component. The system is in a constant state of flux. A slight nudge to one habitat could set off a chain reaction, a cascade of collisions that could unravel the entire swarm in a cataclysm of unimaginable proportions. This is called the n-body problem in physics, and it is famously chaotic and impossible to solve perfectly. To prevent this, the swarm would require a command and control system of staggering complexity. It would need to function flawlessly, automatically, for millions of years. It would need to process quintillions of data points every second, calculating trajectories, gravitational perturbations, and making constant, minute course corrections for every single component. It would need an active system of station keeping, likely massive thrusters on every habitat, to maintain orbital stability. What powers these thrusters? Where does the fuel come from? The maintenance of the structure becomes an energy problem just as vast as its initial construction. It is not a passive monument. It is a machine that is perpetually on the verge of catastrophic failure. It would be like trying to balance 1,000,000,000,000 spinning plates on 1,000,000,000,000 needles simultaneously during an earthquake forever. This is the third great engineering checkmate, the problem of stability. The universe does not want megastructures to exist. They are inherently unstable, temporary deviations from a cosmos that favors dispersal and chaos. The silence we hear could very well be the echo of 1,000,000,000,000 failed attempts, the sound of civilizations reaching for the stars and grasping only the unforgiving laws of physics. Every great investigation reaches a turning point. It is the moment when the overwhelming evidence of an impossible crime is suddenly cast in a new light by a single, overlooked clue. For our engineering investigation, that moment is now. We have meticulously documented the case against us, the crushing burden of mass, the fundamental weakness of materials, the tyrannical energy costs, and the inherent instability of any celestial scale structure. From the perspective of a gravity-bound species, the verdict is in. It's impossible. But we have been examining the crime scene with the wrong set of eyes. We have been thinking like builders on Earth. The clues to overcoming these impossibilities are not found in our terrestrial workshops. They are written in the very fabric of the cosmic environment we seek to conquer. It's time to re-examine the evidence, not as limitations, but as a toolkit. Our first and most vital clue is the nature of energy itself. In Phase 1, we established the recursive energy trap. You need a star harvester to gather the energy to build a star harvester. This assumes that energy is a resource that must be painstakingly generated and stored. But in space, this is not true. A star, our sun, is not a distant, passive campfire. It is a thermonuclear furnace of unimaginable power, and it is actively, violently, and constantly broadcasting its energy into the void in every conceivable form. We are bathed in it. The most obvious form is electromagnetic radiation photons, light. This light carries momentum. It exerts a physical pressure. This isn't science fiction. It is a fundamental property of the universe. This radiation pressure is the first key to unlocking the energy trap. Why? Because it means propulsion can be achieved without propellant. A vast, thin, reflective sheet, a solar sail, can be pushed by sunlight itself. And so what? Why is this a clue, and not just a curiosity? It fundamentally breaks the tyranny of the rocket equation for logistics. We spoke of the insane energy cost of moving trillions of tons of material. With solar sails, the star itself does the moving. We can unfurl sails the size of small moons, attached asteroids we have mined, and gently, patiently push them into their desired orbits over years or decades. The energy is free, constant, and requires no engine, no fuel tanks, no complex machinery. It is an elegant, cosmic scale solution to a brute force problem. But that's not all. The sun also ejects a constant stream of charged particles, protons, and electrons known as the solar wind. This is a river of matter flowing out from the sun, carrying with it kinetic energy and electromagnetic potential. We can deploy vast magnetic sails, or magsails, which are essentially giant loops of superconducting wire. These create a magnetic field that deflects the charged particles of the solar wind. Just like a boat's sail deflects the wind on Earth, this provides another form of free, propellantless propulsion. Suddenly, the problem of moving mass around a solar system is no longer a question of brute force energy expenditure, but one of celestial navigation. It's about building the right kind of cosmic sailing ship to ride the stellar winds and currents that are already there. The star becomes our engine. Our second clue is the construction environment itself, the vacuum and microgravity of space. On Earth, every active building is a battle against gravity. Structures must be designed primarily to support their own weight. We are limited by the compressive and tensile strength of materials in a powerful gravitational field. In orbit, this entire rulebook is thrown out. Gravity is no longer a relentless tyrant. It is a negligible force, a design parameter that can be effectively ignored during assembly. What does this mean for our engineering blueprint? It means we can build structures of a size and delicacy that would be impossible on a planet. Components the size of continents could be assembled with the structural integrity of a spider's web because they don't have to support their own weight. This is the ultimate manufacturing floor. Furthermore, the perfect vacuum of space is not an empty liability. It is a pristine, industrial-grade asset. On Earth, we spend billions creating small vacuum chambers to produce pure materials, perfect crystals, and flawless microchips, free from atmospheric contamination. In space, a vacuum of higher quality than anything we can achieve on Earth is everywhere, and it is free. This allows for manufacturing techniques like vapor deposition and cold welding on an epic scale. We can vaporize an entire asteroid and 3D print its constituent atoms into a perfect, continent-sized mirror for a solar collector, with a flawless finish that would be impossible to achieve in an atmosphere. We can fuse metallic components together with perfect, seamless welds without the risk of oxidation that plagues terrestrial construction. And so what? This means the material science limitations we discussed in Phase 1 are not as absolute as they seem. We can create alloys, crystals, and composites in space that are far stronger and more perfect than their Earth-made counterparts. We are no longer limited to the materials we can create in the chaotic, contaminated, gravity-heavy environment of a planet. The cosmos itself is the ultimate clean room, the ultimate factory. The third clue is hidden in the distribution of matter in a solar system. We assumed we would have to deconstruct planets, a Herculean task. But a solar system is not just a few large planets. It is a vast, distributed cloud of smaller bodies, asteroids, and comets. The asteroid belt, the Kuiper belt, the Oort cloud, these are the universe's pre-sorted, easily accessible supply depots. They are mountains of iron, nickel, carbon, and water ice, just waiting to be processed. And crucially, they exist in shallow gravity wells. It takes vastly less energy to move an asteroid than it does to lift the same mass from the surface of a planet like Earth or Mars. These bodies are the key. They are the raw materials for our megastructure. The engineering application is clear. Instead of planetary deconstruction, we engage in asteroid wrangling. Autonomous, solar-powered robotic mining stations Vaughn, Newman probes that can replicate themselves, would be dispatched to the asteroid belt. They would mine the raw materials, process them in situ using the sun's energy, and use mass drivers, electromagnetic catapults, to launch the refined materials to the construction site in a steady, controlled stream. A mass driver is another piece of our cosmic toolkit. It uses electromagnetism to accelerate payloads to incredible speeds, again, with no need for chemical rockets. It is a gun that fires building materials across the solar system. This creates a logistical pipeline, a conveyor belt of matter powered by the sun, fed by the asteroids, and operated by self-replicating robots. This is how you solve the mass acquisition problem. You don't lift the mountain to your workshop. You move your self-replicating workshop to the mountain and have it send you the finished products. These clues the ever-present energy of the star, the perfect manufacturing environment of space, and the accessible resources of the smaller celestial bodies combine to form a new picture. They transform the problem from one of brute force into one of elegance and bootstrapping. You start small. You build a single solar collector and a single robotic miner. You use that to build 2, then 4, then 16. It is a process of exponential growth, a slow, patient, and inexorable colonization of the solar system's industrial potential. The project may take millennia, but it is no longer impossible. It is merely a matter of time and engineering resolve. The laws of physics that seemed like prison bars are, in fact, the very keys that will unlock the door. We simply needed to learn how to see them. This is the pivotal moment in our investigation. It is the moment we take the seemingly insurmountable challenges laid out in Phase 1 and confront them directly with the cosmic clues we uncovered in Phase 2. This is where the blueprint truly takes shape. The connection, the ingenious insight that resolves the paradox of impossibility, is a fundamental shift in perspective. We must stop thinking about building a structure and start thinking about cultivating a system. The solution to the Fermi Paradox, the design for our galactic beacon, is not a static monument, but a living, dynamic, and ever-growing cosmic organism. Our blueprint is not for a building. It is for a celestial ecosystem. Let's call it the Swarm. Let's revisit the first great checkmate, the problem of materials and structural integrity. We proved that no conceivable material could withstand the gravitational and rotational forces of a rigid ring world or a solid Dyson sphere. The clue we found was that in zero gravity, we are freed from the constraints of self-weight. The ingenious connection is to embrace this freedom completely. We eliminate the problem of structural stress by building a structure that has no structure. The Dyson Swarm is not a single contiguous object. It is a cloud, a flock of billions of independent, coordinated spacecraft. Each component is its own satellite in its own carefully calculated orbit around the star. Think of it not as a spherical cage, but as a cosmic coral reef. A reef starts with a few individual polyps and grows over millennia into a continent-sized ecosystem. It is vast and complex, yet it is made of tiny, independent living things. There is no single structure to a reef that can fail. Its resilience comes from its decentralized, swarming nature. And so what? This conceptual leap solves the material science problem instantly and elegantly. We no longer need impossible materials with infinite tensile strength. The forces on each individual swarm satellite, be it a power collector, a habitat, or an industrial factory, are entirely manageable. They can be built from advanced but fundamentally understandable materials, like carbon composites and metallic alloys refined from asteroids and perfected in the vacuum of space. The structure of the swarm is an illusion created by the precise orbital choreography of its components. It is a triumph not of materials science, but of celestial mechanics and systems engineering. We are not building a bridge. We are choreographing the most complex ballet in history. By redefining the very meaning of building, we have sidestepped a law of physics that seemed to be an absolute barrier. Now for the second checkmate, the terrifying problem of mass, energy, and logistics. How do we fuel the deconstruction of planets and move that mass into place? The clue was the realization that the cosmos provides free energy and conveniently located, low-gravity raw materials in the form of asteroids. The ingenious connection is to create a self-sustaining, self-replicating industrial loop that bootstraps itself into existence. This is the heart of the construction plan, cosmic farming. You don't build the farm overnight. You plant a seed. Our seed is a sophisticated, autonomous robotic package, a von Neumann probe sent to the asteroid belt. This seed has 4 core directives: find resources, use solar energy to power itself, produce finished goods, and most importantly, replicate. Imagine this process. The first probe lands on a resource-rich asteroid. It unfurls vast solar arrays, drawing power directly from the sun. It uses that power to mine the asteroid, refining its metals, silicates, and volatiles. Its first priority is to build a copy of itself. Now there are 2 probes. Soon there are 4, then 8, then 16. This is the power of exponential growth. Within a few centuries, an entire army of automated workers populates the asteroid belt. They are not just replicating, they are specializing. Some become dedicated miners, others become mobile refineries, and a third group becomes the logistical backbone, mass drivers. These electromagnetic catapults, powered by local solar collectors, begin firing pellets of refined materials in a constant, precise stream towards the inner solar system, where the swarm is being assembled. This is our logistical pipeline. The energy problem is solved because the factories are located right next to their solar power source. The mass lifting problem is solved because we are harvesting from low-gravity asteroids. The logistics problem is solved by using the sun's own energy to electromagnetically accelerate the materials to their destination. We have created a self-powering, self-replicating, and self-expanding industrial engine that turns the chaotic rubble of the asteroid belt into the ordered components of the Dyson Swarm. This brings us to the third and most subtle checkmate, the problem of stability. We established that a rigid sphere is inherently unstable, and that a swarm of 1 trillion bodies is a chaotic n-body problem waiting to happen. How does our blueprint solve this? The clue was in the nature of the star's own output, the constant physical pressure of its light. The ingenious connection is to design each swarm satellite not as a passive orbiting rock, but as an active, intelligent statite. A statite, short for static satellite, is a theoretical object that uses light pressure to levitate or hold its position against a star's gravity, rather than orbiting it. Our swarm components will be advanced statites. Each one will have massive solar collectors that serve a dual purpose. First, they collect energy. Second, they act as solar sails. By minutely adjusting the angle and reflectivity of its sails, each satellite can modulate the light pressure it receives from the star. This allows it to make incredibly fine course corrections, to speed up, slow down, or change its inclination. And so, the stability of the entire swarm is maintained not by physical tethers, but by a constant, silent conversation of light. Each satellite is a node in a vast computational network, constantly communicating its position and receiving instructions. The entire swarm breathes, adjusting its position in response to gravitational perturbations from planets or the passage of comets. The star's own light, the very thing the swarm is designed to harvest, becomes the mechanism of its stability. It is a system of active support, where the control mechanism is massless and the fuel supply is infinite. A potential collision between two continent-sized habitats is averted not by powerful, fuel-guzzling rockets, but by a fractional, coordinated tilting of their solar sails over several hours, gently pushing them apart using nothing but sunlight. This is the ultimate elegant solution. The problem of the star's chaotic energy becomes the very tool that creates order. The blueprint for the Dyson Swarm is therefore a trinity of concepts: a structurally decentralized system resembling a coral reef, an exponentially growing industrial engine based on robotic farming, and a dynamically stable choreography controlled by the star's own light. We have found the connections. We have our technical thesis. The impossible becomes plausible. A blueprint is only a dream until the first piece of steel is laid. An investigation is only a theory until it is proven by tangible results. We have assembled our blueprint for the Dyson Swarm, a solution to the engineering problem of the Fermi Paradox. Now, we enter the final phase of our analysis: the construction and the consequences. How would this grand vision unfold, not in theory, but in practice? And what would become of the civilization that dared to build it? This is the climax of our story, the journey from a planetary species to the masters of a star. The construction would not begin with a bang, but with a whisper. In the first century, the great work would be nearly invisible. A series of small, unassuming probes, the seeds of our von Neumann army, would be launched towards the asteroid belt. On Earth, life would continue largely unchanged. Generations would live and die with the project being nothing more than a distant, fantastically expensive line item in government budgets, a dream pursued by a dedicated few. The success of this first phase would be measured not in structures built, but in software running, in the successful replication of the first autonomous miners in the cold darkness between Mars and Jupiter. It is the quiet, patient, and essential groundwork. By the 5th century, the germination would be complete. The exponential growth of the robotic workforce would have transformed the asteroid belt from a static field of rock and ice into a bustling, silent industrial zone. Observers on Earth would now see a subtle change in the heavens, not a grand structure, but a persistent, low-level hum of activity. The first mass drivers, themselves built from asteroid materials, would begin their work. This is the start of the Great Harvest. A steady stream of refined materials, iron, carbon, silicon, nitrogen, would be launched on precise trajectories. A celestial conveyor belt beginning its millennia-long journey toward the inner solar system. There is no fanfare, just the relentless and elegant application of the principles we have laid out. The project is no longer a gamble. It is an industrial process set in motion. The first millennium would mark the first true milestone, the assembly of Helios 1, the very first satellite of the swarm, forged from materials born in the asteroid belt and assembled by robotic arms in a high solar orbit. Its completion would be a moment of profound significance. It would be a continent-sized mirror and energy collector, a single brilliant star in the night sky where none existed before. When its systems came online, validating the principles of energy collection and active stability via light pressure, it would be a proof of concept on a scale that would reshape the human psyche forever. It would be the first thread in a tapestry of unimaginable complexity. This single act would prove once and for all that the blueprint is sound. From there, the weaving begins. Over the next 10 millennia, the process would accelerate. The trickle of materials from the asteroid belt would become a flood. Vast, automated orbital factories would churn out swarm satellites by the thousand. We would see the swarm begin to take shape, not as a random cloud, but in deliberate, breathtakingly beautiful patterns. Perhaps the first phase would be a series of great rings, concentric with the orbits of Mercury and Venus. Then, these rings would be filled in with interlocking constellations of habitats and collectors, like the petals of a metallic flower unfurling around the sun. During this era, the Great Migration would begin. Humanity, its population no longer constrained by the resources of a single world, would begin to move into the newly built habitats. Earth would slowly be transformed, its industrial scars healed, returned to its state as a pristine natural preserve, a living museum of the species that birthed this grand project. Home would no longer be a planet, but a star system. And then, after perhaps 50,000 years of continuous exponential construction, would come the great enclosure. From the perspective of any other star system looking at our sun, this would be the moment our solution to the Fermi Paradox is broadcast to the galaxy. The light from our star would begin to dim, not randomly, but in a structured, artificial way as the swarm reached a critical density. The complex transit signature, the unmistakable sign of a star being shrouded by technology, would be our declaration. It would be an unambiguous signal, a technosignature so powerful it could be detected across thousands of light years. It would be a single, silent, irrefutable statement. We are here. We passed the test. And what is the legacy of passing such a test? It is the birth of a new kind of civilization. The first and most profound change would be the end of scarcity. With the harnessed power of an entire star, the energy available to civilization would be 1 billion times greater than what is available on Earth. Energy, materials, and space would, for all practical purposes, be infinite. The foundational drivers of human conflict competition for resources would become meaningless. This post-scarcity economy would unleash a renaissance in creativity, science, and culture that we can barely imagine. It would be the foundation for a true utopia, not of social design, but of engineering reality. The very definition of life itself would change. Trillions of humans would thrive in habitats tailored to every conceivable desire. Some might live in rotating cylinders, simulating the gravity and environment of Earth down to the last detail. Others might choose to live in zero-gravity spheres, where human biology itself might be adapted for a life of three-dimensional freedom. With limitless energy and computational power, the uploading of consciousness, the merging of biology with machine, and the effective conquest of aging and disease would move from the realm of theory to engineering projects. The swarm would not just be a home. It would be the ultimate laboratory for exploring the potential of life and intelligence. Ultimately, the legacy of the swarm is that it is not an endpoint, but a beginning. It is the graduation of a species from its planetary nursery to cosmic adulthood. By answering the Fermi Paradox with our own existence, we would change the question. The question is no longer, are we alone? The swarm, now a mature and stable system, becomes the greatest shipyard in history. Its infinite energy and resources would be turned to the next great engineering challenge, the construction of starships. Not tiny exploration vessels, but true interstellar arcs, capable of carrying millions of people and entire ecosystems to other stars. The civilization that built the swarm would have the power, the technology, and the will to begin the methodical, patient colonization of the galaxy. So the final legacy is this. The Fermi Paradox is not a paradox at all. It is a challenge. It is the great filter, presented not as an obstacle of destruction, but as a test of creation. The silence of the universe is the silence of the classroom before the final exam. By building the swarm, we are not just shouting into the void. We are quietly and confidently handing in our answer. And we are making the profound statement that the destiny of intelligent life is not to fade away on its home world, but to grasp the fire of its own star and use it to light the way into the darkness. That is the blueprint. That is the legacy. Our investigation began with a question that has echoed through the halls of science and on philosophy for generations. Where is everybody? We stood before the vast, silent cosmos and were met with an unnerving emptiness, a great silence that suggested we might be utterly and profoundly alone. We were detectives facing a crime scene the size of a galaxy, with no clues, no suspects, and no victims, only the haunting absence of our peers. But our core premise, the guiding principle of this entire investigation, was to reframe the mystery. We proposed that the Fermi Paradox was not a failure of biology or a tragedy of sociology, but rather the shadow of the single greatest engineering challenge the universe has to offer. And by treating it as such, we have transformed a haunting question into a hopeful blueprint. Our journey took us through the very anatomy of that challenge. In Phase 1, we stood as terrestrial engineers before a cosmic-sized problem and found it, by every metric we knew, to be impossible. We were confronted by the crushing checkmates of physics, the impossible masses of material, the fundamental weakness of atomic bonds against stellar-scale forces, and the recursive energy trap that seemed to forbid the very first step. The case, it seemed, was closed before it even began. The silence of the universe felt logical, inevitable. It was the sound of universal failure, the default state of ambitious life. But then, our investigation turned. We stopped looking at the cosmos as the source of our problems and began searching it for clues. And we found them hidden in plain sight. In Phase 2, we uncovered the toolkit that the universe provides for free. We found the limitless, propellantless propulsion offered by the star's own light and solar wind. We discovered the ultimate factory floor in the perfect vacuum and microgravity of space. We located our raw materials not in the deep, costly gravity wells of planets, but in the accessible, abundant rubble of the asteroid belt. The prison bars of physics, upon closer inspection, began to look like the very keys to our escape. This led to our breakthrough, the eureka moment of Phase 3. We connected the clues to the challenges and synthesized our technical thesis. The solution was not to build a bigger, stronger version of a terrestrial structure. The solution was to emulate the cosmos itself, to build not a static cage, but a dynamic, living swarm. A celestial ecosystem that grows exponentially, powered by the star it will one day envelop. A system stabilized, not by impossible strength, but by an elegant, active choreography of light and gravity. The impossible monolith became a plausible, patient, and organic process of cosmic farming and celestial construction. And in our final phase, we dared to dream. We laid out the timeline for this grand project, a multi-millennial endeavor that would transform our solar system and our very species. We saw the legacy of such a creation, the birth of a post-scarcity, immortal, and truly stellar civilization. A civilization that answers the Fermi Paradox, not by shouting a message, but by becoming a message. The undeniable technosignature of the Dyson Swarm would be our final irrefutable word in the great cosmic debate. So what have we learned? What is the ultimate finding of this investigation? It is that the great filter may not be the destructive monster we fear. Perhaps the great filter is, in fact, a creative force. It is the final examination for any intelligent species, a test so difficult that it forces a civilization to achieve perfect unity, sustainability, and technological mastery in order to pass. It is the universe's ultimate quality control. The silence we observe is not necessarily the silence of a cosmic graveyard. It could be the silence of the classroom, where countless other civilizations are diligently working on their own final exams. This blueprint, this grand vision of a star encased in a web of human ingenuity, is more than a piece of speculative engineering. It is a mirror reflecting the deepest impulses of our species. It is the same impulse that led our ancestors to stack stone upon stone to build the first pyramids, to arrange soaring arches to construct the great cathedrals, to harness the atom and to reach for the moon. It is the refusal to accept limitations. It is the audacious belief that the universe is not just something to be observed, but something to be engaged with, to be shaped, to be built upon. The challenge of a Dyson Swarm forces us to look at our own world, our own problems of energy, resources, and cooperation, not as insurmountable barriers, but as small-scale versions of the same engineering test. It teaches us that the only true path forward lies in long-term thinking, in sustainable systems, and in the belief that technology, wisely applied, can solve problems that seem impossible. We may not begin building a Dyson Swarm tomorrow, but we can begin to think like the people who will. So we end where we began. Where is everybody? The answer our investigation provides is that they are not to be found in a single radio message, a fleeting whisper in the cosmic storm. They are to be found in the patient and monumental act of building. The true sign of intelligence is not a word, but a world of its own making. The silence, then, is not an absence. It is an invitation. It is the pristine, untouched canvas of the cosmos, waiting for a species with the vision, the will, and the engineering courage to make its mark. The question is not whether it is possible. The question is whether we will choose to be the ones to do it. The blueprint is here. The silence is waiting to be broken.